Okay, so first one, orthogonal decomposition theorem. Let's take a look at it. So the first one, okay. Orthogonal decomposition theorems is the generalize uh the concept to the construct the basis. Uh, so think about this. So here, let's say this is the subspace W, and let's say this is the y hat. Okay, and then that's this is a vector. Oh, that's a vector y. Okay, then we know that the component of the y on the subspace W is this, right? That's the y. Okay, we know that y hat is the projection, right? Projection of y hat onto W, which is y hat, right? Dot, and then the if you say the vector, so this is vector u, and this vector u over u dot u and the vector u, right? This is equal to sometimes we can I mean the bottom one is the norm, right? The norm L2 norm square in the vector u, and then sometimes the inner product can be uh denoted by y bar comma u for using angle bracket. That's the inner product of two vectors, nothing but this. Okay. Is the norm L2 norm? Is it see the 6.1? Okay. Then they'll introduce the norm. Okay. Now so but what if the subspace is not, you can see that those subspaces are out too, right? Just plain. But if we want to find out y minus y hat, this is y minus y hat, right? Y minus y hat, right? If you want to find out the such a vector, which is the shortest, right? The vector from the y to w and just the higher dimension of space, right? So for orthogonal decomposition theorem is talking about that. Okay. So first one, I mean orthogonal decomposition theorem, the statement is this. So let W, this is given, okay, be a subspace of Rn space, okay, all right. Then for each, okay, then for each vector y in Rn space, okay, can be written uniquely in the form uniquely. The form y bar is equal to y hat plus vector z. Okay. So here y hat is in the vector in a column vector in a Rn, right? The y hat, sorry, not Rn, the W, right? This is in W, and then vector z is in W complement. Complement. Okay. And then if we know the basis or basis W, subspace W, then we can express the y hat as y, this is dot product, okay? Let me use sigma, okay? Sigma notation, y bar, dot product u1 over norm u1 the square u. Oh, it should be j, not j, not j. J goes 1 through the p. Okay, so here, what are the u1 through the uj? Is a basis, orthogonal basis. J is an orthogonal basis. Oh, back W, subspace W. Okay, UP, sorry. Okay. So now then, it means that Z is equal to what? Y minus Y hat, right? Okay. So what is Z then? In this figure, that's a Z, right? Y minus Y hat. So the vector Y hat is called the orthogonal projection of Y onto W. We know that, right? This is what? That's orthogonal projection, actually, not just a projection, but orthogonal. Projection of Y onto W. Now we just generalize orthogonal projection. Okay, so how can I find out? I mean, so in in 2D, the W in this figure, the subspace is in an R3, and then actually W is a plane. So it's easy to figure out the orthogonal projection of this vector Y onto the subspace. But when you generalize, then what does Y hat look like? This. Okay, generalizing the space to Rn, not just R3, Rn, and then W is W is a subspace of Rn. Okay, this Rn subspace. Okay, then Y hat is not just a single term of the this is a projection. I mean, the projection, orthogonal projection of one single vector, but this is summation, the sigma sum of this one projection, actually orthogonal projection, and then U1 through UP or orthogonal basis. Okay. All right. Now then, so it means that Y hat, I mean Z, Y hat can be Y hat is a linear combination of orthogonal basis with a weight. This is the scalar projection, right? Scalar of the orthogonal projection. Okay? So we can say this is weight. Okay. Here's a proof. All right, so let's say the U1 through the UP be orthogonal basis. Okay, this is given. But how can you find out? We'll see. That's a Gram-Schmidt process, but okay, let me just say, okay, so U1 through UP orthogonal basis is given. Okay. Okay. Now Y hat. So what do we want to prove? We want to prove that what? Y hat is Y is can be written as Y hat plus Z. Okay, and then that what this is unique. Okay, for given vector Y, that can be expressed as Y hat plus Z, and then that is unique. This form is unique. That's what we want to prove. Okay, so for here, and then the first one, the second one, define Y hat. Ooh, sorry, Y hat is this. Okay, what they define Y hat as like this. So the linear combination of orthogonal basis with a scalar projection. Okay, I'm not gonna rewrite this one, repeat writing this one again. Okay, so just skip it. Okay, then Y hat is in the subspace W, right? Because what this is, I told you, linear combination of the orthogonal basis of W. So definitely Y hat is in W, right? And then next one, let's say z is equal to y minus y. Okay. Right. And then since du u1 through the up are orthogonal, right? I mean, u what? Bar I dot per u j bar equals 0, right? I is not equal to j, right? So which means so that since this one, we're going to use the property of the orthogonal. Okay. So then z times dot product of u1 is equal to z is what? Y minus y bar, right? Y minus y bar dot u1, which is equal to y dot u1 minus y dot u1 over u1, and then okay, sorry, let me just sigma, and then y at dot uj, j goes 1 through the p over the uj square, then uj. Dot product of u1, right? So this is equal to what? That is, this one can be simplified as well. Because I told you, you know, ui dot uj equal to 0 if I is not equal to 0, I is distinct to j. Then this summation will be simplified by what? I mean, only the term when j equals 1 will be non-zero. Other term will be 0, right? So this is equal to y in the u1 over, and then u1 square, and then u1 dot u1. And then all other terms going to be 0 because of that property. So this is equal to, okay, so now here that is equal to, so y dot u1 minus what? Look at this, what's that? Dot product of same column vector is what? This is equal to u1, the square of L2 null, right? Discrete L2 null. So the denominator, this is scalar, right? Norm is scalar. So denominator will be canceled out this one, right? So numerator and denominator, yeah, numerator will be we're gonna get numerator only, so we just copy this one here. So y and then dot and then u1. This equals 0. Okay. So z dot u1 equals 0. Similarly, we can show that what z dot u j is equal to 0, and then j goes yeah, so 1 through the p, isn't it? Which means that the vector z is orthogonal to every single orthogonal basis of the subspace W, right? Which means that z is in W complement space, right? So similarly, so now thus z is orthogonal. Let me use this one, which means that's orthogonal. Z is orthogonal to uj, and then j goes 1 through the p, right? So it means what? Vector z is in what? W complement. Oops, I just keep the transpose. Okay. Okay. So yeah. And now next one, I'm going to show the uniqueness. Okay, that decomposition. So this is decomposition, right? So what's what? We just decompose the vector y as the linear the sum of two vectors in W and W complement, right? So that expression is unique. That's what I'm going to show them. Okay. What I did was to show that Z is in W. We know the W complement. We know that Y hat is in W, right? But I just showed that this is in W complement. Okay. Now that expression is unique. That's what I'm going to show them. So, okay, suppose that, okay, so, I'm going to use just conventional way to prove the uniqueness. So what are you going to do? So, yeah, so, suppose that what? Vector Y can be decomposed as other vectors, Y1 hat plus Z. Okay. So Y hat 1 is in W, and then Z1 is in W. This is W complement. Okay. Right. Then what? Then we suppose that okay, there are there is other vectors that can be so that Y can be expressed as like this sum of two vectors. Then what? We have to show that some contradiction or two vectors Y1 contradiction, or we need to what? Need to get the this result Y1 is equal to Y and Z1 is equal to C. Okay, either one. Okay. So I'm gonna show that this. We suppose that this one and then blah blah blah, and then at the end we got this. Okay. That's a symbol of a contradiction. Right. Yeah. So Y then what? Y hat plus Y1 hat is equal to what? Z1 plus Z plus Z1, isn't it? Okay. And then what? Y and Y1 are in W, right? So this is in what? W. Because the sum of two vector must be in the subspace W. And then since Z and Z1 are in W complement, the sum of two vector must be in W complement. Complement. Okay. So if we say that Y minus, right? Sorry. Subtraction, sorry. So let's say Z, not V, into V is equal to Y hat minus, Y hat minus Y hat 1. Okay. Then this is in W. But what? V is equal to what? Z minus Z1, right? That is in W complement, right? Thus, V dot V must be equal to what? 0. Right? So it means that what? Y hat minus Y1 hat is equal to 0. Right? So Y hat is equal to Y1 hat. And yeah, and what? Z minus Z1 is equal to 0, so Z is equal to Z1. So I proved that. Okay, so let's see example. That's example 1 textbook. Okay, so let's say U1 is given as column vector 2, 5, and -1. Okay, and the U2 is a -2, 1, 1. Okay, and Y is given by 1, 2, 3. Okay. All right. So guess what? I want to decompose Y as a vector in a W and then W complement, right? So what are you going to do? We need to find out Y hat which is orthogonal projection of y, and then we need to find out z, right? The first one, second one. So the question is to decompose y as a definitely this is in R3, right? So that is in W. W is subspace of Rn. Okay. So we want a question is what? Decompose y as y hat and z. Okay. This is in W. This is W complement. You know. Okay. Example one. The solution is this. Y hat by the orthogonal decomposition theorem. Y hat gonna be linear combination of U1 and U2. Yep. So we gotta find out dot product of y and u1 and y and u2, and then also we find the norm, discrete altonorm of u1 squared, discrete altonorm of u2 squared. Okay, so doing that, then it turns out that this is equal to negative 2/5 to 1/5. Okay, so since we got this one, that this number by the linear combination u1 u2 and then u1 u2 are orthogonal bases. I didn't mention the problem example one, but u1 u2 are orthogonal bases of w. So this is trivial. It's obvious that y hat is in w. Okay, then how can you check that z is in w complement? Then to show that we show that z dot product to z and u1 and z and u2 0. Why? That means what? Z is orthogonal to u1 and u2, since the u1 and u2 are orthogonal bases. So every single vector in W can be generated by u1 and u2. So that means Z is in W complement. Okay, so doing that, yeah, it's easy to figure out that these two dot product turns out to be 0. So Z is in W complement. Okay. Okay, next one, best approximation theorem. The best. Okay, so the statement is simple. Okay, so let's say W be a subspace Rn. Okay, be a subspace of Rn space, and the first one or second one, Y be any vector in Rn space, and third one, let Y hat be an orthogonal projection of Y. Okay, this is orthogonal projection of Y onto W. Okay. Okay. Then what? The norm of Y minus Y hat, okay, is less than Y minus V. Here V is for any vector. For any vector V in W. Okay. So which means that what? Which means that this 1, 2, 3 here, the vector Y hat is the best approximation to Y by elemental Y. Okay. So give me a second. Then Y, the vector. What does that mean? Here, this guy, this is the best or the closest. Closest vector to Y bar. Okay. So now then that is the best approximation. Okay. But why? Sorry. Why here? Why here is the best approximation? Okay. Prove it. I don't want to prove this. Okay. All right. It's okay. Prove. Prove. So take a plane right here. Okay, let me think about the R3 space. I know, okay, let's say, I know this looks like a plane, but assume that W is Rn space. Okay, this is Rn right here, and the W is a subspace of Rn. Okay, so now this right here, let's say vector Y, then here's this, yeah, let's say this is a position vector, kind of. Okay, zero vector right here. And then, we know the orthogonal projection Y is maybe right there. Okay, so this is gonna be Y head. Okay, right. Then this is gonna be Y minus Y head, right? This distance. This can alter now. Okay, I just keep the writing the subscript, the two in the subscript. Right, let me think about the other vector. Just arbitrarily, I just pick the vector right here. So this is a vector V. That Y minus Y, V gonna be this. So it's gonna be Y minus V. Right? Okay. All right. So as you can see that definitely Y minus Y head is a shorter than the distance Y minus V, right? We can see that, but I want to prove this one in mathematically. So Y head minus V, okay, is in W, right? So Y minus V is in W, yep, because Y is in W, V is in W. Right? Then by the orthogonal decomposition theorem, okay, by the theorem, Y minus Y head is orthogonal. This is orthogonal to W, right? Okay. Now that means that what it means that Y minus Y is orthogonal to every single vector in W. Since this guy is in W, so we can say this is orthogonal to this. So Y minus Y hat is orthogonal to Y hat minus V. Right. Now then next one, since Y minus vector V, okay, it can be expressed as, we use some trick. We want to express this one in terms of that one. So Y minus Y, I just subtract this, and then add Y hat, because Y minus Y hat plus Y hat is 0, right? So we just, that means it's nothing but we add a 0 vector. Now we apply the Pythagorean theorems. The Pythagorean theorem of the norm is this. Y minus vector B. This is the alpha norm. Okay, this is equal to Y minus Y hat square, put the square, plus Y hat minus vector B. Okay. All right. So this is definitely what the norm is greater than or equal to 0. this one is greater than or equal to 0. This one greater than or equal to 0. Because keep in mind is every single move is great a positive. Okay, and not negative. Sorry. It means that this one must be less than what? This one, right? The proof is done. Okay, so but why this is a Pythagorean theorem? This is a general version of Pythagorean theorem. Look at this. This we got the right triangle, kind of. So the y minus v, y minus v, right, is equal to y minus y bar plus, and then y minus y hat square plus y minus v. Right? So now then, the we move to this one of orthogonal, no, Gram-Schmidt process. Okay, let me skip the example. This one, look at it by yourself. And then the next one is Gram-Schmidt. This is the main theorem in today's class. Now we want to find out the basis, orthogonal basis, okay, from the using the orthogonal decomposition theorem. Okay, so let's see example first one. Let me see example first one. Example, 1 second, B1, B2.